Okay, good morning, everyone. Soon we will start. I shall share screen. Okay, I hope all of you can see this. So this is the last slide of last class. So where we finished proving that theorem concerning the finite state space and aperiodic positive recurrent Markov chain on a finite state space. And there we got some information concerning the rate of convergence or geometric rate of convergence. So today we shall briefly look at what are called time reversible Markov chains. And some of these kind of things have come from engineering and physics, I think, those kind of Markov chains. Okay. So let Xn be an irreducible positive recurrent Markov chain with transition probability matrix P. I mean, state space need not be finite. And let us say pi is a stationary distribution. We are not assuming aperiodicity. So the stationary probability distribution need not be the limiting probability distribution. Okay. Suppose the initial distribution itself is pi. That is x0, it's distributed as pi. Then from an earlier result that we have proved, each xn also has the distribution pi. That is, the distribution remains stationary, it doesn't change. If it starts from the stationary probability distribution, the distribution doesn't change. I mean, the random variables xn's can be different, and Gin-Rengel will be different, but the probability law is the same. Now, for any n greater than or equal to 0 and j in the state space, observe something which is going to be a sequence of equations. So to fit that into one slide, I have also started that sentence here. So note it down if you want. Okay. Say in this, because the length of the slide is rather limited, certain things are going out. So I'll tell you what those are when we come to that step. So sort of there, you can make out. So probability xn equal to j, given xn plus 1 equal to I, n plus 2 equal to, I2, and n plus k equal to ik. Instead of calling this as I1, we are calling it as I, because the j and I will have a special role here. And these are used, the symbols, because the 2 will correspond to this 2 and k like that. So this is a probability of an event, let us say xn, that is at time n. If you consider that as a present time, these are certain things given in the future time, so-called future time, n plus 1, n plus 2, and n plus k. So now write down by definition of conditional probability, this is be equal to probability of xn equal to j, xn plus 1 equal to I, and then xn plus 1, n plus 2 equal to I2, etc., etc., x sub n plus k equal to ik, divided by probability of what is occurring in the denominator, so to say. Not denominator, the conditioning event. that is probability of xn plus 1 equal to I, xn plus 2 equal to I2, and xn plus k equal to Ik. So to sort of keep the thing in the proper perspective, let me tell you what we are going to do to the denominator here. The denominator, we are going to write it as, say, xn plus 2 equal to I2 up to xn plus k equal to Ik, given xn plus 1 equal to I. So that comes here. And therefore, since this is the probability of the intersection, it will be this conditional probability multiplied with probability of the conditioning event, namely xn plus 1 equal to I. And in the numerator also, we do something similar. We are going to write it as probability of xn plus 2 equal to I2 up to xn plus k equal to Ik, given these two. That is that given xn equal to j and xn plus 1 equal to I. That you only see part of it. And that conditioning event itself consists of two parts, xn equal to j and xn plus 1 equal to I, and that way split it into probability xn equal to j multiplied with probability xn plus 1 equal to I given xn equal to j. So that is this step. In this step, we are going to use the Markov property. The numerator, look at this part. This is this k minus 1, this thing time points, the given that xn plus 2 equal to I2 up to xn plus k equal to Ik, that given xn equal to j and xn plus 1 equal to I. So if you apply the Markov property, that xn equal to j goes away. So you get only that event given xn plus 1 equal to I. So in equating this to this, we have applied Markov property. So once you do that, this guy, this entire guy, and this part in the denominator, they cancel each other. So that is the advantage. So once they cancel each other, then probability xn equal to j is pi j because of what we have seen in the previous slide. Each xn is distributed as pi. And then this is nothing but pi sub ji. At n point it is at j and n plus 1 I, pi ji. And the denominator, this and this cancel. So you are left with just this one, and that again is pi I. See, this notes will be uploaded today. So that is why I am making. So this you can see there. In the notes, these things are coming in full. So in other words, we have got some kind of a thing concerning if given an event in, let us say, in the present, and assuming that the future points are known, what is the probability or conditional probability? For that, we have got some handle. Okay, now this what is given here in the right side, please copy it down. Yeah. Now what occurred on the right side of this equation, we denote it as P star or P asterisk ij. Be careful with the, see here it is P sub ji, it is P asterisk sub ij. Verify that this is a stochastic matrix. So that means if you sum for keeping I fixed, if you sum over j, what happens? So if you sum over j, this is unaffected. What you have in the numerator, since pi is a stationary probability distribution, summation over j, pi j, p j I is pi I. So that gets cancelled, so you get 1. So I have done the verification orally using the fact that pi is a stationary probability distribution. So since this is a well-defined stochastic matrix, by the way, in all these things well-defined is because since we are assuming it to be a positive recurrent Markov chain and so on, the stationary distribution if pi is a stationary distribution, pi sub I is strictly positive for every I. So that ensures that this guy is well defined. So then by the general kind of wisdom from measure theory, which has been endowed in this, we assume that there is a time homogeneous Markov chain Yn on the state space S with this as the transition probability matrix. And its initial distribution Y0 is also pi. Remember that this was the kind of thing we had assumed to sort of generally say that we will assume that the Markov chain is well defined or it is completely described if the transition probability matrix and the initial distribution are given. We really don't have to mention a particular experiment or example where that kind of a thing can arise. Mathematically, we are assured that those are proper objects. Note it down. Yeah. So this new Markov chain Y sub n is called the time reversed Markov chain associated with our earlier Markov chain. And both cases, the initial distribution is the same. Y0 is pi, x0 is pi. Note it down if you want to, please. Okay. So this, what we have discussed, these 3 slides, we can interpret as follows. If treat the stationary distribution as the initial distribution and sort of view the future as known and the past as unknown. In other words, the roles of future and past are interchanged. Time goes in the reverse direction. That is why that time reversible kind of thing. Then still the Markov property still holds with P star as a transition probability. Note it down if you want. Okay. So that leads to your definition. So let pi be a stationary probability distribution for a Markov chain Xn with transition probability matrix P. So the Markov chain Xn will be called time reversible if pi I multiplied with Pij is equal to pi j multiplied with Pji for all ing. Note it down if you want. Of course, if each pi j is strictly positive, and if the Markov chain is time reversible, then the P star ij is Pij. This definition doesn't require pi I to be strictly positive. So we are not assuming the Markov chain to be positive recurrent here. So if the Markov chain is time reversible and positive recurrent, then pi star ij, which we had defined earlier, yeah, this is the same thing as Pij. And consequently, if since x0 and y0 have the same distribution, and since they have the same transition probability matrix, they will have all the finite dimensional set. Sorry, note it down. Okay. So the condition for this time reversibility, this equation, this is called the set of detailed balance equations. What is the meaning of that? See, remember, if when we say stationary probability distribution, if x0 is distributed as pi, each xn is distributed as pi. So in other words, if the probability distribution pi describes as the kind of, as let us say xn moves x1 to x2 to x3, the various kind of the concentration of particles or mass, that total balance or total this thing doesn't change if it is a stationary probability distribution. That means that overall behavior, the probabilistic behavior remains the same as the Markov process evolves. Here, something more is happening. You take any two states, I and j. So since pi is assumed to be the distribution, pi I can be considered as the kind of probability or mass at I. And Pij is the probability of these things which goes from I to j in one step. So this can be treated as the rate of flow from I to j in one time point. And similarly, pi j pji is something concerning the rate at which the process moves from j to I in one step. So if it is time reversible, this is equal to this. So there come kind of a balance at a small scale, you may say microscopic scale. Whereas stationary probability distribution is something which happens in the big, the macroscopic. So these are called detailed balance equations, not just overall balance, namely the probability measure or distribution remaining stationary. By the way, this kind of thing I have taken from Sheldon Ross's book. While Pottenstone doesn't discuss time reversible chains, or I'm sort of guided by the Sheldon Ross. Okay. So we will prove a small proposition. Let Xn be an irreducible positive recurrent Markov chain with stationary probability distribution pi. So suppose we have the following. Starting from any state, so any path back to I. Of course, there will exist because it is positive recurrent and so on. I communicates with I. So from I, there will be a path going to I again, coming back to I. So if that path passes through, let us say I1, I2, Ik, you come in the reverse direction, the reversed path. Then the probability of the reversed path is same thing as the probability of the original path. In other words, if the path is I to I1, I1 to I2, and Ik to I, you consider the reverse path I to Ik, Ik to Ik minus 1, and so on, I2 to I1, and then I1 to I. So these are the respective probabilities of one-step transitions. Pi I1, Pi I1 I2, and so on. And this is equal to, this is the, for the one-step things in the reverse direction. So if these two probabilities are same for all possible I1, I2, Ik, and all I. So then the proposition says the Markov chain Xn is time reversible. Note it down if you want. Of course, here we are saying any Ik and also for any possible Ik. You can go from return from I to I in 10 steps, or it may be possible in 11 steps and things like that. For each K. So we will prove it. In the proof, we will use this equation, but then go one step further. Instead of calling the last thing as ik, we are going to call it j. But the other things will also be I1, I2, ik. Okay. So let us say I1, I2, ik, and then j is one path. Then the reverse path is I to j and j to ik and so on. And finally I1 to I. But you sum over that equation only over I1, I2, ik. Only these indices. J, you don't sum over j. So I hope you had time to copy this down. Writing down, just be careful. Okay. So that is basically saying as this summation is p to the k plus 1 and entry is ij. Ijth entry of the matrix p to the power k plus 1. And of course, this is pji. And similarly, here you have p to the k plus 1 sub ji. Okay, note it down. So now next step, we are going to sum these things over k running from 0 to n minus 1 and also divide by n. And that p, sorry, in that next things, somehow this side has become the left side and that has become the right side. Sorry. Yeah. This is what you found there on the right side. So p sub ij and then summation k going from 0 to n minus 1, p to the power k plus 1 sub ji. And here also something similar, pji and then here ij. And what we have here is our old friend. See here k is running from 0 to n minus 1, which means k plus 1 is running from 1 to n. So this is nothing but 1 over n times g sub n ji. And similarly, here it is 1 over n times g sub n ij. Yeah. Note it down. So you are given that the xn is a positive recurrent Markov chain and pi is a stationary probability distribution. So pi j is strictly positive for every j. And if you go to the limit here, you get Pij pi I equal to Pji pi j. And this precisely is the condition for time reversibility. Only thing is pi I have written here, Pij I have written here. Yes. So what we have done in this thing is, this criteria, that is each reversed path back to I has the same path as the forward path, the probability, they have the same probabilities. That is a sufficient condition for Markov chain to be time reversible. It turns out that condition is also a necessary condition. Verify that for k equal to 2, k equal to 3 and things like that. So that is the last slide for the day. And if you want me to go to any of the other slides or any questions. And Monday we will start with martingales, discrete parameter martingales.
Monday we will start with what?
Martingales.
Okay. Discrete parameter martingales.
Yes, sir.
Okay, so is the class over?
Yes. I'm waiting for just in case somebody wants to see some slide or ask any question. The Ehrenfest model is the reversible Markov chain that you will find in the problem sheet. Okay. So we will end the session today and we will meet again on Monday. Take care, all of you.